So previously, we have spelled out the steps in the Kalman filter recursions. And in fact, those steps we've derived work for any model which is specified in terms of transition probability of xt to xt minus 1, and then an observed variable which just depends on the associated latent variable at the same time point. They work for any distribution that you could plug in for those models. And in this slide, what we're now going to do is start to consider what we would need to compute in the case for the linear Gaussian state space model. So we're going to substitute in the distributional forms for the transition probabilities and for the likelihoods. Okay, great. And we have previously talked at some length that for the linear Gaussian state space model, these filtering distributions will be Gaussians. So the actual things that we're going to manipulate in this algorithm when we come to implement it on a computer are going to be the means of those Gaussians and the covariances of those Gaussians. And we're going to need a little bit of bookkeeping to keep track of these different Gaussians, because there's going to be a few of them that we're going to have to manipulate. One of them associated with the prediction step, for example, that first step of the Kalman filtering algorithm shown in the middle of the slide here, and another one associated with the filtering distribution at the next time step. Okay, so the way I'm going to notate that is as follows. The way we're going to keep track of that is as follows, is each filtering distribution, so here's the filtering distribution at time step t minus 1, is going to be a Gaussian over the variable here xt minus 1. And I'm going to notate the mean and the covariance here by two sets of indices. The subscripts are going to indicate the variable which this is a distribution over. So let me just be completely clear about that. The subscript here, which I'll ring in orange, the t minus 1s on both the mean and the variance here, are going to refer to the variable that that distribution is over. And the superscripts here, so these t minus 1s on the top, they're going to refer to what data has been used to compute that mean and that variance. So what y's are used. So here we're using all the y's up to including t minus 1, and so we get t minus 1 in the subscript, in the superscript, I should say. Okay, so that's our notation, and I hope that's going to be clear for people. Let me just erase it so we can sort of clearly read that from now on. Okay, so we've got this filtering distribution. On a computer, we'll just store the mean and the variance of it from time step t minus 1. What we have to do first is make a prediction for what xt is going to be, a little forecast based on our current filtering distribution. And the way we do that is we take the old filtering distribution and we diffuse it through the probabilistic dynamics here. And the cartoon picture of this is shown here. Okay, so because everything's linear and Gaussian, this is going to give rise to a new Gaussian. And now the Gaussian is over xt, and it's using variables 1 through to t minus 1. So following our rule introduced above, the superscripts of the new mean here are t minus 1, referring to the y's that have been used, and the subscripts are t, because the distribution is over variable xt. Okay, so we just, in order to implement this step, we just have to compute this new mean and this new variance, or covariance in the general multidimensional case. So how do we do that? Well, this probabilistic dynamics, we know the equation for this is probability of xt given xt minus 1. This is equal to a Gaussian distribution xt with a mean that is given by a matrix A times the previous value of x and adding correlated Gaussian noise on. And here we can use all of our tricks for manipulating Gaussians that we've polished through the course. So I can rewrite this actually as xt is equal to a plus a times x of t minus 1 plus some noise, where the noise is distributed according to a Gaussian with mean variance and covariance q. So this is an equivalent way of writing that equation that we've talked about quite a lot. And so to compute, let's say, mu t minus 1, we just need to take the expected value of x of t here. And because of the rules of nested conditional expectations, we can write this as the expected value over A, x of t minus 1 plus the noise. And this is just A times the expected value of x of t minus 1 plus the expected value of the noise. And now we can substitute in for these things. So the expected value for the noise is just 0. So this thing goes. The expected value of xt minus 1, well, it's the mean of this distribution. So this thing is just mu t minus 1, t minus 1. And that gives us our new mean. Okay, so the way that new mean, our new updated mean, our forecast for the mean at the next time step is just our matrix A times the old mean, sort of a really intuitive result. Okay, so that's computed the means. Let's compute the covariance as well. So in order to do that, I need to compute what the expected value is of xt transpose. And then we can take away the mean in order to compute the covariance. So let's give ourselves a little bit of room for doing this. We're going to need some extra room. So I'm going to carry out this calculation in this little space here. Okay, so expected value of, let's zoom in a bit. Let's make this a bit clearer. Expected value of xt transpose, I can write as the expected value. Let's substitute in the formula for x of t, expected value of A times x of t minus 1 plus the noise times A xt minus 1 plus the noise transpose, this thing. And now we can multiply this guy out. It's just a quadratic form. We get A times x of t minus 1. Let's get this bit over here, x of t minus 1 transpose, A transpose, plus, now the cross term between the noise and axt minus 1, the thing that we have two lots of, that's going to have 0 expectation because the noise is independent from x of t minus 1. It's added after x of t minus 1. So although we get two lots of this quantity, two lots of expected value of the noise times x of t minus 1 transpose A transpose, this expected value is going to vanish. The cross term is going to vanish because of the independence assumptions. And the mean of the noise, I should say, is 0. That's why this is vanishing. Independence and mean 0 of the noise. Okay, great. And then there's one third term here, which is just the expected value of that noise quantity times itself. This thing. Okay, and now we're almost ready to go in and fill in these things. Let's do one final thing, which is to take this expectation inside, because A is deterministic. We can write this as A times the expected value of xt minus 1 transpose times A transpose, and then this term up here. Good, okay, so this is just A times the expected value of xt times x of t minus 1 transpose. And this thing is the covariance of the noise. And the covariance of the noise is given by this equation down here. It's just equal to Q. And we're almost home and dry here to compute the covariance. The last thing we have to do is, in order to get the new covariance, is substitute off the mean here at the next time step. We've computed the expected value of xt times x of t transpose. We need to subtract off the mean times the mean transpose. And when we do that, that means let's give us some space here. I don't need this equation anymore. We don't need this one anymore. We can define v t minus 1 as equal to expected value of xt transpose minus mu t minus 1 mu t minus 1 transpose. That's just a definition of the covariance. And when you do that, we can take this expression here for the mean. So we get A times expected value xt minus 1 transpose A transpose plus Q minus A mu t minus 1 t minus 1 mu t minus 1 t minus 1 times A transpose. So that's substituting this thing into the second term if it wasn't obvious. And now what you notice is we can take these two terms involving A here and A transpose, and I can bring them inside. So I can take the mean inside this thing. And then hopefully that's obvious that that will produce the covariance at the previous time step when I combine those two together. So this will just look like A times the covariance V t minus 1 times A transpose plus Q. Hopefully, although this was long-winded, this result looks really familiar to you. It's just the result from taking a Gaussian with a particular mean and covariance and passing it through a linear transformation plus noise. Then the new mean and the new covariance are just the linear transformation of the old mean. And then for the covariance, there's this sort of canonical form where it's linear transformation times old covariance times linear transformation transpose plus the covariance of the noise. It's a formula that you'll have met a lot in a lot of different contexts, actually. It just looks more complicated in this case because we've got lots of different variables and things are depending on time, so on and so forth, but it's nothing more than that result. So for the forecasting step, you just need to implement the two equations, which I'm going to highlight here. Let's highlight them in purple. It's this update for the covariance and this update for the mean. Okay, these are the actual two things that you need to implement on a computer. Good, okay, and this just formally writes those down. And this, as we said before, for many cases, or at least the scalar case, you can think of this first term, if everything's set up to be stationary, as just diffusing the mean towards 0. And the second term you can see is going to increase the variance. It's going to take the old variance and make it a bit wider. It's essentially convolving with a Gaussian. So that's this, the origin of this schematic before, where you take the black Gaussian and you make it a bit fatter and therefore a bit shorter, and you move it towards 0. Good. Okay, so that's sort of a fairly full exposition, actually, of the forecasting step or the prediction step of the Kalman filter. Let's now look at the second step, where you integrate the new likelihood, multiply the new likelihood by the prior, and renormalize to give you the new filtering distribution. Now, deriving this essentially is a mechanical exercise. It involves taking the Gaussian likelihood and the Gaussian forecasting distribution given up here, and completing the square, and then writing down the new mean and new variance of the new Gaussian. And just to remind people, so it's absolutely clear, probability of yt here given x of t, this thing is a Gaussian, if you remember it, is specified by them in the model, where the mean is just a matrix C times x of t, and the noise is a matrix R. So C and R will be entering into the equations in this step. It's a pretty long-winded derivation, and it's not one that I think conceptually leans too much here. You've done a lot of completing the square if you've followed the questions associated with the course. And so I'm just going to state the results here. So first off, our notation, this is the new filtering distribution. It's over variable xt here. So we have t's as subscripts, and it is involving all of the data up to the current time point. So in the superscripts, we've got t's as well. So this is our new Gaussian that we're forming at this step. The values for mu and v in this Gaussian are given by completing the square, and they're stated here. So this is not something I would advise learning. This is something that you just need to sort of look up when when you need it. Let's just talk a little bit about the mean update here to try and give some intuition for what's going on. And it comprises two terms. So the new mean is equal to the old mean. This is the mean coming from the prediction or forecasting step up here, just this mean here. The second term is a correction term. And the correction says, take the observed variable y of t and subtract off this quantity. This quantity is your prediction for y of t based on the previous time step, because it takes the previous, or the estimate for the mean of x of t. This is the estimate for the mean of the x of t based on the older information. And then it passes it through the matrix that relates y of t. Remember, y of t is equal to c times x of t, the matrix c times x of t, plus some Gaussian noise, where the noise has covariance r. So if we take the mean estimate for this and pass it through the matrix C, we get our most probable or mean estimate for for y of t. So the correction term here takes the discrepancy between what we thought the value of y was likely to be and the actual recorded value for y. And if that difference is really big, we make a big correction. And if that difference is really small, we make a small correction. And this prefactor k, this thing is called the Kalman gain. And it's computed using this update down here as well. And it sort of controls the strength of that update and will depend on things like the observation noise. So the observation noise is very big. If there is a discrepancy, well, that was sort of expected. So we won't change our mean very much, because we know that each data point doesn't give us much information. But if the noise variance is very, very small, if R is very small here, then the Y's carry lots of information about X, and we make a bigger correction. Okay, so that's some effort to lend some intuition for what's going on here. Again, our schematic picture where our new filtering distribution is now tighter than our forecast, because we've gained the information from the current observation y of t, and the mean will lie between the mean from the likelihood and the mean from the filtering distribution. Those intuitions also hold as well, and are embodied formally in these equations. Okay, so this is the sort of the most technical we're going to get about this. This is probably one of the most challenging bits of the course, but the good thing is you don't really need to remember all the details here. You just sort of need to keep your eye on the big picture and make sure you understand what's going on. Just taking a step back, what you would need to do to implement this thing on the computer then, as we said, is implement those two equations for the forecasting step, and then these equations for the update step. So just 5 equations, and of course there's some jiggery pokery you need to do for the initialization. Great. In the next video, we're just going to look through a quick demo of this in action and show you sort of visually how the Kalman filter looks.